and work through our answers. So we're going to start with fluorine. Fluorine has how many electrons? Sorry, I forgot. 9. So we'll put our first electron in. The first electron goes where?
1s.
The 1s. Where's the next electron? 1s. Next electron.
2s.
Next electron.
2s.
Next electron.
2p.
Next electron.
2p.
And
2p.
and
2p.
where am I? 1, 2, 3, 4, 5. Okay, I'm there. Okay. Haha, I heard you. Good joke. Whoever said that. Okay.
I was over here.
So it is a bit repetitive to specify the location of every single freaking electron. You aren't going to like doing that. So let's condense. This can become 1s2, saying that there are 2 electrons located in the 1s orbital. There are 2 electrons located in the 2s orbital. There are 5 electrons located in the 2p orbital. We'll look at that a little bit later too. Okay, so why is this start to become a bit interesting? As we went from the 1s to the 2s, we only put 2 electrons in. Why did we all of a sudden jump to 5 electrons for the 2p?
That's how many are in the people.
Remember, every time we move up in energy, we get a new type of orbital home. It doesn't say how many homes we just get a new type. So when we move up to the second energy level, I get 2 types. One of those is S, one of those is P. To figure out how many actual homes or orbitals are in each of those types, I now have to look at the quote-unquote orientation. Well, what did the S orbital look like? A sphere. If I rotate a sphere, can I tell it was rotated? No. So there's only one orientation for a sphere, which then means there is only one orbital for an S type. Because there's only one orbital, I can only put in 2 electrons. What happens when I move to the p orbital? The shape changes and I get a dumbbell shape. If I rotate the dumbbell, can I tell it was rotated? Yes. This now introduces the concept of our orientations. The p orbital has 3 possible orientations. Because there are 3 possible orientations, there are now 3 orbitals. Each of those single orbitals can hold 2 electrons, which means when I look at the p-type orbitals, I can hold a total of 6 electrons. But what if I look at a p orbital? How many electrons can I hold there? 2. A single orbital can only hold 2 electrons. A type of orbital is now looking at that entire class. Okay? Questions about fluorine? Okay, now the exciting one. I may have to do this one all the way at the bottom so I can fit it in here. Arsenic. First electron. A 1s orbital. Second electron. 1s. So I'm going to just go straight to our simplified notation, 1s2. Okay? Next one. Next one. Next one. Why'd you jump to 3s? Okay. We got a couple answers. Our chart helps us out on that. Okay? On saying we shift to the 3s. There's a... Go ahead. This chart is not on the test, and the reason why is it's already given to you on the periodic table. 1s, your first row, corresponds to the number in front. When I move to the second row, I'm looking at 2. So my first row, I have hydrogen and helium. How many elements in the first row? 2. How many electrons could I fit in the 1s orbital?
2.
Wait, it's the same number? How many electrons can I fit in the second energy level?
2.
Second energy level is only corresponding to anything with a 2 in front. How many electrons fit? 8. How many columns?
Well,
get
the
10.
other one is
No. That's not the second energy level. That's the first energy level.
Only the second.
Only the second energy level. How many columns are in the second row? 8. It's the same number. Okay? The periodic table gives you the fill pattern. Okay? Just a sec. So we fill our 1s. Where's the next electron need to go? It would become 3, right? Element 3 is located where? The second row, so its energy level is 2. The second, or these two columns collectively are referred to as the s block because the electrons are in the s orbital. So in that first column, I'm at 2s1. I moved to the next one, I've added an extra electron. Am I in a different energy level? Nope, still the second energy level. Am I in a different orbital? I'm still in the s block. No. So it becomes 2s2. What happens when I add another electron? I need to become 5 electrons. Way over there. I'm now looking at boron. Which energy level? 2, because it's in the second row. Am I in a different orbital type?
Yes.
Yes, I'm no longer in that block. This block is collectively known as the p block because the electrons go into the p orbitals. Okay? So boron becomes 2p1 at its outermost. What's the next one? Carbon, 2p2. We erased that electron configuration. It was there. Fluorine, 2p5. Count out your columns. 1, 2, 3, 4, 5. Each of those columns corresponds to adding an electron. Okay? When we hit our 2p6 with neon, the next electron makes us go to 11, which is now over here, which is located in which row? Third row. Which block is it in? The s. So that first electron is going to go into the 3s orbital. Next one. 3s2. Oh, thankfully I can put my arm back down. Next one. Now I got to pick it back up again. 3p1. Okay, are we at arsenic yet? Good answer. Remember, Ar is argon, not arsenic? We add one more electron. We would go to element number 19. Find 19 for me. It's in the fourth row, s block, 4s1. The next electron does not go into the 3d. Weird. Don't we have the d orbitals available? Yes. Do we put electrons there? No. Why not? Symmetry. You may not like the symmetry argument, which is entirely up to you, but it is a symmetry argument coming out of this. It is more symmetric to have a single electron in the s orbital than to have a single electron in 5 possible orbitals. Okay? Much more symmetric that way. Okay? You don't like the symmetry argument. That's fine. Memorize periodic table. It tells you. S block, first column. There it is. Don't like the periodic table? That's cool. Memorize this. Those are your options. Understand what the periodic table is giving you or memorize it. Okay? Yet again, periodic table, tons of information. If you want to spend your time to memorize that data, that is fine with me. I don't care. That has no skin off my nose. That will hurt your exam score because you're wasting brain power. But that's not me. Okay? Next electron. 4s2. Here's the tricky part. Where's the next electron? I add one more electron to 20, I become 21. I'm now in the D block. Okay, and this is where things get funky. Which row are we in? The fourth. So we might reference this as the 4D, and unfortunately we'd be wrong. Okay? And we go, why did we offset it? Because we're trying to memorize or not memorize the electron fill patterns by shifting it off by 1 on the periodic table. The fill pattern is already given to us. We don't have to think about it. We do have to realize that our d orbitals are offset by 1. But that's it. So that very next electron goes into a d orbital that happens to be in the third energy level. Okay. Next electron. Still the 3D. And that will continue all the way on until we hit to zinc, which gets us 3d10. Why can I have 10 electrons in the d orbitals? There's how many orientations? 5 orientations, which gets us 5 orbitals. Each orbital holds 2 electrons, hence the 10 columns of the d block. Add one more electron past zinc, and I become 31. Good answer. The other element is gallium. Where's that electron located? It is in our p block. Which row? Our 4th row. The S and the P blocks are set up perfectly with the rows. The D block is offset by 1. Guess what the F block is? Offset as well. Okay? Do you have to worry about the F block? No, because I'm not going to ask you about it, so don't worry about it. All you need to worry about right now is the D block. Okay? We add another electron. We'd become 32, which is element germanium. And we'd have 4p2. We're still not there. We need to add one more electron. 4p3. We now have the electron configuration for arsenic. Ta-da!
So if someone was like talking to a chemist and they said 4p3, you would have to know that was...
So there's an interesting question. When we go through and look at this, okay, number one, and people addressed this already, that's a lot of crap to write. I completely agree with you. That is way too much effort. I don't want to write that down every single time. Okay? So we can come up with some simplifications. The first simplification, what was special about this last column on our periodic table? Noble gases. What was characteristic of all of our noble gases? They don't. We can kind of look at don't look at need any more electrons. They're inert. They don't react. Okay? They are fully saturated in their outermost shell. So what we can go back and do is take a look at all of these things here and say, where did I fill up? That entire section from 1s2 to 3p6 corresponds to which element? Argon. So instead of writing out each and every single one of those, I'm going to say, tired, it's argon. Okay. Is it just argon, or does it have more electrons? It has some more electrons. What are those more electrons? 4s2, 3d10, and 4p3. And I've now done the exact same thing. Big longhand or shorthand. You wanted to do osmium at element 76. What would our abbreviation immediately jump to? I'll accept Xe, also known as xenon. Now I just have to account for an extra 20 electrons, as opposed to having to account for all 76. Okay? So the shorthand is just a way to kind of cut some of that down.
We can only do that with the gases.
And the gases are the only one that we'll use that standard notation on, okay, for shortening it. Okay? So back to your question, could we just refer to 4p3? So if I said element 4p3, what would you tell me?
You're crazy.
Crazy is fair enough. You might presume that I'm saying every other level is full. Okay? But can electrons move from one energy level to the other? Say if we pump a bunch of electric current into them? Yeah, they can. So I can't refer to it as just 4p3. I'm going to have to get a little bit more detailed in that answer and saying everything else is full. I'm not exciting electrons anywhere. Okay? And I'd also have to reference that I'm at a neutral state, because that's also an important aspect. Okay? These are all neutral at this stage. Okay? So the next part is we might want to reference some of these electrons as being our important electrons or our unimportant electrons. Okay? The argon electrons, actually let's step back from that. I take arsenic and I now move it towards another element. What electrons are going to interact on arsenic? So that's really what I wanted. I don't want to hear valence yet. The outermost electrons are going to be the first ones to interact because they're on the outside. So let's name those outermost electrons because those are probably most relevant to how I'm going to make bonds. And then structures, chapter 12. So what can I do? I'll refer to the outermost electrons as my valence electrons and my innermost electrons as the, what's the middle of the Earth? The core electrons. Okay? So now when we go through and look at our configurations, most chemists will just reference the valence electrons because those are the outermost ones. Those are the ones most likely to interact. Those are the ones most likely to do weird stuff. Okay? So we tend to focus there. Questions about that? Okay. Which of the elements on the periodic table are you responsible for determining electron configurations? Officially, all of them. That's a bit mean. I don't want to deal with F. Okay? And even the d orbitals, I think, can be a kind of a pain because as we continue up in our energy level, what happens? So here, 1s to 2s. Okay, that makes sense. To 2p, that makes sense. 3s, that makes sense. 3p, that makes sense. 4s. Okay, well, let's just accept it. One exception. 4s. Okay, 3d, 4p, 5s. Oh, okay. Well, there must be another exception. Okay. So then I move back all the way down to 4D, 5P. Ah, seriously? Okay. The fill pattern starts to get all sorts of weird the further down into the periodic table you go. Why? That comes back to looking at our energies. The higher up in energy we get, what happens to the distance between the individual energy levels? It gets smaller and smaller. So now how do our electrons fill? According to symmetry, not just energy. Okay? That's why we start getting these odd fill patterns the further down the periodic table we get. Which is why I want to avoid all of those pretty much altogether. You are responsible for the electron configurations from element number 1 up to element number 36. All of those are fair game. Okay? So those of you trying to do some practice, hey, here's a practice question. 36 practice questions. Electron configuration for hydrogen through krypton. Awesome, there you go. Have at it. Okay. Within that, you can reference your valence electrons or your core electrons. Our chemical properties are largely based off the valence electrons. Okay. So let's throw one more curve in here. So we haven't had enough curveballs. People watching nomenclature video should be able to tell me the oxidation state on oxide, or the symbol for oxide. What is it? It's O, oxide. Hydroxide is OH. Oxide is just O. O2 is oxygen. O negative 2. What is the electron configuration for oxide? Spend some time. Ready for the answer? I would say drum roll, but that's not really necessary. Thank you. Our answer is... Oh, it's there. There's our answer. Done.
I was right. You said I was wrong.
I didn't say you were.
Where's all the 1s, 2p, all that junk? I can condense it all into the electron configuration for neon. Done. So how did we do that? Okay. Oxide. That's the oxygen element. The oxygen element has how many protons? 8. So we look at the number of protons times the charge. What's the charge on a proton? +1. And our charge is now based on the balance of protons and electrons. So what is the charge on an electron? -1, right? How many electrons are there in just oxygen? 8. Which gets us what charge? 0. Balances out. Did I ask you for oxygen? No, I asked you for oxide. What's the difference between oxide and oxygen? Okay. The other one, or oxide, has a negative 2 charge. It's not neutral. So how do we get that negative 2? And this is the part that everybody seems to freak out on. And the reason why you freak out, believe it or not, is right here. Okay. If you remember back when we were looking at conversions, I said, remember minus signs? Minus signs will haunt your dreams through all chemistry. This is where it's coming in. Okay. Everybody goes, well, all I need to do to get the 2 is I need to remove 2 electrons. Okay, let's test it. What happens? Plus 1 times 8 plus, what's the charge on an electron? Negative 1. It does not change. If I lose 2 electrons, how many electrons would I have? What does that then equal? A positive 2. Is that what you were trying to solve for? No. You did the wrong thing. So instead of removing 2 electrons, add 2 electrons. So our electron count for the oxide is 10 electrons. Set up our electron configuration. 1s2, 2s2, 2p, 6. Good check. 2 plus 2 plus 6 is 10. We've got our total. What element happens to correspond to 1s2, 2s2, 2p6? Neon, our noble gas. There it is. We can just write the neon electron configuration, and we have our answer. What we have just identified was that one ion had the same electric configuration as another element. O minus 2 had the same electron configuration as neon. Okay? Same electron configuration is a mouthful. I don't want to say that every single time I want to talk about this relationship. So I'm going to use some Greek or Latin or whatever it is. And same happens to be iso. An electron configuration will become electronic. So I'm referring to 2 elements having the same electron configuration as isoelectronic. That's all it means. Same electron configuration. Okay? Questions on our electron configurations?
Yes. I'm sorry, but I am lost with the neon. I mean, I got the bottom part, but
So the bottom part,
Yes, I got that.
okay, how many electrons is that?
10.
10. Find the element that matches 10 electrons.
It's neon, but
There it is. That's it.
But what will happen if I just give you the...
Both answers are correct.
Okay, either or.
Both answers are correct. Yeah, one answer is the ultimate, hey, I'm lazy and I don't want to do this. It's still correct. The other answer is, I need to make sure. The other answer is, I need to show all the individual steps, which is fine.
Is it minus 2 or is it 2 minus? Does it matter?
Good point. You'll notice that your textbook, and I seem to be the only one that does this, and I still don't understand why, because I think my way makes more sense. Why not? Remember we talked about egotistical scientists? You were supposed to agree with that. Thank you, guys. I appreciate that.
Yes on the inside.
If we look at how we can write oxide, you'll always see me include the charge first, then the magnitude of that charge. So I will write minus 2. The textbook and most science things will write the magnitude of the charge and then the sign on the charge right after. The difference? Nothing. There is no difference. So don't stress about it. Okay? Why do I include the charge first? Because the charge is ultimately what's going to allow me to decide how that interacts. The number is irrelevant. The sign on that charge is really important for looking at reactivity. If I find a negatively charged element, what do I need to do? What should it be attracted to? A positively charged element. If I have a 2 element, what is it attracted to? I don't know, is it positive or negative? Okay. The number doesn't mean a whole lot because it doesn't allow you to bulk classify out your separate categories. The sign on the charge or the sign of that charge is a lot more important for classifying things. So I've got it organized according to importance, at least within my head. All them other chemists are wrong.
When you did the calculation, where did
Yes.
you get the plus 1 from? Where did that come from?
The plus 1 in the initial calculation. So the calculation I did was the number of protons times the charge on the proton. What's the charge on a proton? Plus 1. Okay. Because we're looking at the balance of those charges.
I have a question. What would happen if you have like oxygen plus 2?
Okay, good question. Here it is. Can't even name this one because the species doesn't exist, but it works. Electron configuration for O plus 2. Well, how many electrons would we have?
4.
6 electrons. 8 was our neutral state. To get to a plus 2, I have to lose 2 electrons. So I get 6 electrons. My configuration becomes 1s2, 2s2, 2p, 2. Which, whoever said that, is isoelectronic with carbon.
Both carbon.
Okay.
Wait, so you can only do the bracket thing with...
So the bracket approach should really only be applied to our noble gases. Okay. We can still make any comparison with isoelectronic. That happens to be the electron configuration for
Oh,
what?
so you just do that with isolate?
Carbon. Yeah. Okay. So for that osmium example, just because it's there, an acceptable notation would, osmium's got 20 electrons I want to look at, so I'm not going to go all the way out. But our acceptable notation for osmium would be to start with xenon and then look at the rest of the electrons. Okay? That is an acceptable electron configuration for osmium, with whatever all those other ones are, and I don't want to count them all out. A bad electron configuration for osmium would be this. Okay, and then what is it? 3d4? 1, 2, 3, I think it's 4.
It's not wrong, though.
Or not 3. It's 5. Is this still the electron configuration for osmium? Yes. It does not appropriately use the rules for your brackets for your electron notations. Okay, so your shortcut for electron configurations has to use your noble gases. When looking at isoelectronic, you can do whatever comparison you want. Okay? Questions? And away we go. So, chapter 5, here's our big summary that we already talked about. Once we've got our electron configurations, we can now start to group our periodic table according to sections. We have our S block, our D block, our P block, and our F block. This can help us build our electron configurations. It can help us find the outermost electrons relatively quickly, like a game of Battleship. Okay? Relatively sensical. Any questions on that? Okay, so let's spend a couple minutes. So question 1, reasonable density given the data. How do we figure it out? Figure out where potassium and all those elements show up. Potassium needs to show up between sodium and rubidium. What is a value that is between those? 1.25. Would 1 work? 1 is between those two values. It is, but do you have more information? As we move from lithium to sodium, it goes up by 0.4. As we go from rubidium to cesium, it goes up by 0.4. So our potassium should be somewhere in that range. It clearly can't go up exactly by 0.4 because then we start to get too close to the rubidium. So we might just average that distance and hit somewhere at the 1.2 range. Perfectly acceptable. How many electrons fit in one p orbital? Follow-up question. How many electrons fit in the d orbitals? This is one of those stupid reading comprehension questions, being very, very careful with the question you answer. In question 2, how many electrons fit in one p orbital? So some extra things to jump on. 1, and there is no s. That means I'm only looking at a single orbital. Does it matter what orbital it is? No. All orbitals hold 2 electrons. That's it. How many electrons fit in the d orbitals? Notice the plural and the lack of the word 1. This is now referencing the entire d class. Within the d class of orbitals, how many electrons can I fit? 10. How did you know that? One way, memorize. Ideally, you're not doing that. What you're doing is remembering the D block and counting the columns in the D block. Okay? That might be finding our error, because remember you guys had a hard time counting up to 12, wasn't it, last time? You beat me because I went up to 3 and ran out of problems. Okay? So up to 10, there's 10 columns, which means 10 electrons in the d orbitals. Okay? Why does the atomic radius increase down a column? Okay. So we can jump to the quick answer. There's more electrons. We go from hydrogen to cesium in that first column. Hydrogen has 1 electron, cesium has 55. Which one's going to be bigger? Cesium, because a lot more electrons. So that makes sense. Okay. Why does the atomic radius decrease left to right in a period? So hold on to your thought for question 4. You said more electrons means bigger. What happens when you go from lithium to neon? You get more electrons. And yet the atomic radius decreases. Are we looking at just adding electrons to an atom to change the radius? No. It is where those electrons are being put. We look at the outermost electron for lithium. It is located at what energy level? The second energy level. The outermost electron for cesium? 6th energy level, because it is in the 6th row. Where is the 6th energy level relative to the second energy level? Much further away. Because we're putting more electrons in isn't just the answer. We're putting those electrons in a higher energy level. Why does that become important when we look at 5? The electron for lithium goes into what energy level? The second energy level. I didn't ask the type of orbital, I just want to know the energy level. Neon's last electron goes into what energy level? The second energy level. I'm putting the electrons into the exact same energy level, which means what should happen to the radius? It should not increase. It shouldn't really even decrease, because I'm putting electrons at the same place. Same place means same distance. That's what same means. But it decreases. What else is changing? Not in the orientation, unfortunately. Not a bad guess. As I go from lithium to neon, symmetry. I am changing the number of electrons. I am changing symmetry, but that's also not going to matter. I'm adding protons. If I take the north and south end of a magnet, okay, and I line them up in this fashion, right? There's an attractive force there. Okay. If I put another north and south end of a magnet, am I going to have the same attractive force? Assuming it's the same type of magnet. Yeah. What happens if I now take this magnet and I make it stronger? Does the force change?
Yes.
Yes. That's why our radius decreases. The nucleus becomes more positive. Our electrons are going to the exact same distance away, but now the nucleus is becoming a stronger magnet. What does that do to the electrons? Suck them ever so slightly closer. By coming closer, your radius has now decreased. There's your explanation. We cannot explain that trend until we understand electron configurations. You don't like that explanation? Cool. Don't worry about it. You can miss those questions on the test. Memorize the trend. Because you will have multiple choice questions asking what happens to the trend. Okay? You don't need to explain it. You need to be able to answer a multiple choice question. Okay? So, when we're looking at our radius, we can see down a column, we're moving up to higher energy levels. Higher energy levels, necessarily further away. That's why it gets bigger as we go down a column. Left to right, the electrons go at the exact same energy level. Okay? Lithium goes in at the 2s second energy level, or 2s. Beryllium, 2s. Boron, officially the 2p, but which energy level is that? It's still the second energy level. Those are all going in at the second energy level, which means they aren't getting any further away from the nucleus. If anything, they're staying the exact same distance. But now our nucleus becoming more positive will suck the electrons slightly closer. And in this case, if we take a look between here, we see some pretty significant differences in those distances. Okay? Shameless plug for organic chemistry. We only memorize one trend down the column. Left to right, we just say they're all the same size. See? Organic. It's easier. Just don't talk to any of my students about that. Okay. Questions about our trends for atomic radius? Okay. Next one that pops up in your textbook is this idea of ionization energy. So before we even evaluate trends, we have to know what it's talking about. Ionization energy is the energy required to remove an electron. Okay? And the important part of this is removing the electron to the vacuum. So if we went, and this is going to cause headaches for people watching at home. That's why you should go to class. To remove an electron to the vacuum. Our vacuum is here. Whatever. If we have an electron here versus an electron here, which electron requires more energy to get it to the vacuum? Red or purple? Red. Why? It's a much larger difference in distance, which means more energy. So how are we going to determine our ionization energies? Look at the electron configurations. Where are your highest energy electrons? How much energy does it take to remove that electron to the vacuum? So the trends in ionization energy strictly come from electron configurations. Just down here. So our trends. The ionization energy increases as you go from the bottom to the top in a group. So as we go from cesium to lithium, why would it increase? Where's lithium's highest energy electron? It's in the second energy level, so it's very, very close to the nucleus, very low energy. Where is cesium's? The sixth energy level, really far from the nucleus. So it's going to be stupidly easy to remove an electron from cesium, because it's like, I can't even see that thing out there. Right? Really short distance. So your ionization energy will increase as we go up the column. How about left to right? Okay? As we move left to right, our ionization energy also increases. Why? What happened to the radius left to right? It got smaller left to right, which means the energy to remove that electron is now even more. So we can use our understanding of our atomic radius trend to actually predict our ionization energies. And how do we get all of our ionization energies on our atomic radii predictions? Through electron configurations. Am I recording? Yeah. Sorry. The next part is you see this in general statement pop up. Right? In general. In general. Okay, we're not talking about the military. Why the in general? I appreciate the plug there. It's referring to in theory because there are exceptions to that trend. And everybody goes, oh my God, there's an exception. I got to memorize an exception. Absolute nonsense. There is no exception to it. Look at the electron configurations. The electron configurations will tell you what you should do with the ionization energy. So where's our first exception? Lithium goes up to beryllium, and all of a sudden our ionization energy drops for boron. Huh. It didn't just go straight up. Why is that an exception? Look at the electron configuration for beryllium. Outermost electrons for beryllium. What do we got?
2p1.
Beryllium is Be. 2s2. For boron? 2p1. Okay. Let's actually look at our valence. So for boron, it would actually be 2s2, 2p1. What happens if we remove an electron from beryllium? What's its electron configuration? 2s1. What happens when we remove an electron from boron? 2s2. Remember that symmetry argument? 2s2, fully saturated, nice and full. Both halves of the face are present. Remove an electron. The most attractive person you're aware of just lost half their body. Are they still attractive to you? Ouch. Okay. And the vertical axis, not the horizontal, right? Okay. That might change your opinion. We've lost symmetry. So we started awesomely beautiful, symmetric, and now we're dead. Okay, well, I guess you could be into that too. No judgment. Okay, so not a good thing. Does beryllium want that to happen? No. So what happens to its ionization energy? It's going to go up because it doesn't want to lose that electron. What happens to boron? Here, 2s2, that's nice and symmetric. What happens to the p? How many p orbitals are there? There's 3 p orbitals. How many of those p orbitals have an electron in them? Only 1. How symmetric is that? Not at all. So we are starting boron's electron configuration as ugly. What happens when it loses an electron? Beautiful! Boron's like, hell yeah, get rid of that electron, now I'm hot. Okay? That's what's happening with our ionization energies. It's not just, oh, it increases, it decreases. No, it comes from the electron configurations and looking at how they break. Okay? Move to the next one. What's the next one? I think it's nitrogen and oxygen. Boron, carbon, nitrogen, oxygen. Nitrogen. Electron configuration for nitrogen. 2s2, 2p3. Oxygen.
Hold on, be symmetrical about it.
Ira, why are we skipping?
The one that's
All we really need are our valence electrons. Why? When we're going to rip our electron away, we're going to pick which electron? The highest energy electron. So I don't care about the core electrons. So we could drop a helium configuration in there, but I'm out of space. So what happens to nitrogen when I rip an electron away? I become 2s2, 2p2. Oxygen. Anybody see anything obvious there? If you don't, that's okay. I honestly don't think it's obvious. What do the p orbitals look like? 1, 2, 3. If I look at nitrogen's ground state with all of its normal electrons, it's 1, 2, 3. How symmetrical is that outermost electron shell? Each of them are half full. Okay, so yeah, it may be half a body, but at least it's half a body. Okay. What happens when we go to oxygen? Ooh, which was more symmetry? Nitrogen or oxygen's ground state? Nitrogen was much more symmetrical. What happens to nitrogen when I remove a single electron? Is it more or less that word? It is less symmetric. Does it want to become less symmetric? What happens to its ionization energy? It should increase. What happens with oxygen? Oxygen loses an electron and it becomes more symmetrical. What does oxygen say?
Yeah.
Hell yeah. What happens to its ionization energy? It goes down. There's the drop. That's what's happening. It's the electron configurations. It's not some messed up rule that you're told to memorize. It's looking at the electron configurations. How many of you are confident in electron configurations? Those of you that are confident don't need to memorize jack when it comes to rules. Those of you that didn't raise your hands, welcome to memorization. Sorry, that's the way it is. Okay. Sort of. Questions on ionization energy? Okay, the next one I'm only going to float out here really quickly. Whoops. Actually, yeah, that's a good question. What charge does the atom become after we've ionized it? It should become positive. We've removed an electron. So it's lost an electron. Everybody goes, well, it lost. Why is it positive? The charge is an electron.
Negative.
Negative. We lost debt. We lost a negative. We're now positive. Okay? There's again that nasty negative. And in fact, in this case, it's a double negative.
But if you're only removing one electron, you still have electrons left over, isn't it still considered negative?
So yes, it's positive, remember, not negative. Okay? Its new charge would be positive.
Okay.
Is it positive 1, positive 2, positive 3, positive 4, positive 5? It's only positive 1. So we can now add extra information to that and say how big is the positive. By only losing one electron, we're going to become positive 1. Electron affinity. This is only in the textbook, or opposite of that statement. It is only on the slides. It is not in the textbook. Electron affinity is the opposite of ionization energy. The electron affinity means our atom reaches out into the vacuum and grabs an electron and brings it into its structure or its electron configuration. Okay? So we can look at the ability for an atom to grab electrons and hold on to them. Okay? Is that going to be important? Well, when I bring two atoms near each other, what starts to interact between them first? The electrons. If one of those atoms is like, give me that electron, what happens? It takes it, and we start to form a bond. Okay? So it is really important to think about electron affinity and ionization energy. What charge does our atom become? If we look at electron affinity, becomes negative. We're looking at the ability for an atom to grab electrons. It's becoming negative. Okay? We could go through and look at those trends. Not a huge issue, but the reason why I bring this up is that if we look at the balance of electron affinity and ionization energy, and we kind of average them out, what we end up with is something known as electronegativity. Okay? Electronegativity is the ability for an atom to take bonding electrons away from another atom. Okay? You might say, well, why do I care about this? Well, when you looked at nomenclature, we had two nomenclature systems. We had an ionic and we had covalent. How did you know you had an ionic compound? Metal and a nonmetal. Why do we name ionic compounds differently than our covalent compounds? Look at our covalent compounds. They're electronegativities. They're all really, really high. What is the difference in electronegativity for all of those compounds? Really, really, really small. What happens when I take a nonmetal and a metal? The difference in electronegativity now is massive. So when I bring those two atoms near each other, the nonmetal grabs the electrons away from the metal, and the metal says, peace, take it. Is that going to change the bond characteristic? Yeah. If we look at two nonmetals, they now come up to each other and they both want to grab the electrons, but they both have the same strength. So what happens? They just kind of go, yeah, okay, I'll kind of share with you because I don't want to get beat up. Okay? And we get a different type of interaction. That comes from electronegativity. We've instead spun it as metallic character. What is metallic character? Completely made up. Electronegativity at least has some basis in science and some numerical identity to it that allows us to do some pretty awesome calculations. Okay? Incredibly important, we'll keep coming back to it. Your most electronegative element is fluorine. Your least electronegative element is cesium, down in the opposite corner. What was your most metallic element? Hint, it rhymes with rhesium. Cesium. And our least metallic? Fluorine. The trends are opposite each other. Excuse me. This is an important thing to use if you have to move into any more chemistry, or particularly any chemistry that matters, like organic chemistry, biochemistry, for that matter, biology. It's electronegativity. That's how you predict how molecules interact and react with each other. Massively important. So, next part. We talked about ionization energy and electron affinities. When we looked at ionization energy, it was the ability to remove an electron. Okay? When we removed the electron, what charge did the atom become? Became positive. We take a look at our ionic charges. Which elements are positive? All are far left. All are our metals. What was the interesting characteristic about our ionization energy? Ionization energy, not electronegativity. What happened to our ionization energy as we moved left to right? It increased. Meaning the elements on the left, really easy to give up an electron. Elements on the right, F you, I'm not giving it away. Which meant, interestingly enough, they did not become positive. They become negative. Well, how did they become negative? Well, we'd have to look at electron affinity. Why did the textbook not mention it? Because they didn't think you could think about it. Okay? Fair enough. Let's look at it a different way. Okay? Of all of those elements, which ones do you not see charges on? Noble gases. Why not? It's not that they have no valence. They definitely have valence. Their outer valence electron shell is filled. Their entire energy level completely full. You can't put any more electrons in. Which then means, should they be able to react? No. Because to react, they have to be able to give up electrons. Do they want to give up electrons? No, because then they become not symmetric. Okay? So when we look at fluorine, fluorine's electron configuration, we'll go all the way out. 1s2, 2s2, 2p5. Fluorine's like, yeah, I can react. I got this empty hole. If I can fill this hole in my life, I will be happy forever. So what does it do? It reaches out and it finds another element that has electrons and it takes them from it. What happens to it when it takes those electrons? Becomes an ion, and that ion becomes F minus, which happens to equate to which electron configuration? Neon. Why does it want to look like neon? Perfectly symmetrical, no longer reacting. The charges that you are told to memorize, the reason they have those charges, they're trying to look like the noble gases. That's it. Take a look at fluorine. What are the noble gases closest to fluorine? And there are two that I'm looking for. Neon and helium. To look like neon, what does fluorine need to do? Gain one electron. To look like helium, what does it have to do? It has to give up electrons. How many does it have to give up? It has to lose 8. To look like helium, 6. 7. 7. 7's the answer. We're all bad at math. That's good. That's horrible. Okay. So which is easier to do? Gain 1 or lose 7? Gain 1. So what does fluorine do? Gains 1 and becomes a -2 charge. Take a look at oxygen. Oxygen can look like neon or helium. Which is easier to do? Gain 2 electrons or lose 6? Gain 2. What charge does it become? -2. Nitrogen can look like neon or helium. To look like neon, what does it need to do? Gain 3. To look like helium? Lose 5. Which is easier, gain 3 or lose 5? Gain 3, charge is -3. It's not on here, so let's test it. Let's see if this theory actually holds. What's that next element? Carbon. What does carbon need to do to look like neon? Gain 4 electrons. What's the other one? Which is easier to do? They are both equal, which means both happen. Which means we don't have you memorize it because too much crap can happen. That's why. Lithium. What are the elements that lithium could look like? Helium and neon. To look like neon, what does lithium have to do? Gain 7 electrons or lose 1. Which is easier? Lose 1. Okay. What we are trying to do when we look at these charges that we're having you memorize is that we're trying to make them isoelectronic to our noble gases. That's it. Okay. Coming from your electron configurations. Do you want to memorize the electron configurations? No. Should you know how to use them? Yeah, because that gets you all these. Okay? Or you get the periodic table, and we try and pull some more information out of it. Because you're like, well, I don't want to memorize that. So I'm going to say that first column is +1. That second column was what? Nitrogen, -3, -2, -1. -3. And actually, we got to do it the other way around. Take your column that you're in. For nitrogen, you're in column what? 15. Minus? Gets you? -3. Oxygen, you're in column 16. Minus? -2. 17 minus 18? -1. 18 minus 18? 0. What else can you do? It's not up there. Never mind. It's a different trend. Okay? That information is already on the periodic table. You have access to it. All you have to do is take advantage of it. Okay? Questions about that? Okay. Yeah, we'll just whip through these. So, Chapter 4 summaries. Please pack up, because we are done. So I'm just going to kind of sort of talk over you. Chapter 4 summaries. There are some cool scientists that you are responsible for knowing. Dalton, Thomson, Millikan, Curie, Rutherford. You will see questions on those. You are responsible for knowing those scientists' names and what they studied. Okay? What information did they get us? Subatomic particles. You have protons and neutrons. What are their charges? What are their masses? Wave nature of light, discrete versus continuous. This kind of gets to your memorization question. Bohr, another scientist to remember. Was a discrete gentleman. Drum roll, thank you, right? Discrete because that's what he's known for, not because he was born. Discrete energy levels, which gives us our electron configurations, which are our orbitals. Subatomic particle with our electron, all of those. You need your electron configurations, your valence shell. Chapter 5, Mendeleev periodic tables and predictions, trends based off of our electron orbitals, chemical physical properties, atomic radius, ionization energy, and ionic charges. We will pick up with Chapter 12 on Thursday, which is all about drawing Lewis structures. It takes practice. Work with it.